All right, 5 o'clock. Guess we'll get started. Today's meeting is going to be about learning the grid security essentials. If you haven't already, join the Discord with the role and sign in. In today's meeting, we're going to be first talking about a Cyberforce competition put on by the DOE. Then we're going to be going into actually learning about what the heck is the grid, and then we're going to go into the GridSecSim, which is the project that we're doing for the whole interest group, and going through how to actually contribute to that and the kind of workflows associated with that.
So the Cyberforce Department of Energy competition, it's hosted in Illinois, right outside of Chicago. We have an interest form for people to, if the people are interested in joining the team. We are working with the department right now, as well as GridSec, to get funding for hotels and whatnot. Still haven't completely figured out how much we're going to get, but that's kind of in progress right now. The competition is not like your normal cybersecurity competition, especially since it's OT based. You have an AWS environment where, as the blue team, you're defending an assumed breach scenario. So you get access to the AWS environment 10 to 12 days before the actual competition. This is kind of where you build, secure, and test your systems prior to the actual competition. As I mentioned, it is an AWS environment, so there's a lot of things like EC2 instances, a VPC, which is like a virtual private cloud. So a lot of knowledge in AWS is good for this, as well as knowledge about OT, of course. There's PLCs, CNCs, and different kinds of industrial control systems. The Obsidian Rift Energy Company is the this year's scenario. They have a different one each year. This one's like an oil rig that's off the Pacific Ocean. So yeah, that's just a little bit of a brief overview. We're gonna go more into it when we actually have a team together, talk more about the competition. They do have a lot of free resources on the actual competition, like a 101 library that has information about everything that's a part of the competition. But yeah. So going into the actual grid security, kind of more of the compliance side of the house before we actually talk about the grid. So a little bit before we go into the compliance part, just a little bit of a background. So there's been some pretty big attacks that have happened on different grids. So of course, the Ukraine power grid attacks. There was recently the Danish energy compromise, as well as the Firewall North American power grid cyber attack, which just kind of took out the power for 5 minutes. And with the increased electricity consumption in the U.S., the grid is even more important. And as you can see there, the utilities has the most amount of weekly cyber attacks out of really any industry. So it's kind of important that we secure it properly. So there is a lot of electric grid compliance standards. The North American Electric Reliability Corporation or something like that has the CIP standards, the Critical Infrastructure Protection Standards, and that is kind of enforced by the Federal Energy Regulatory Commission, and they approve and enforce these NERC standards. And then you have the Department of Energy C2M2, which is the Cybersecurity Compatibility Maturity Model, and this is kind of a voluntary model, so you don't it's not mandatory, but a lot of electric utilities do use it. And then you have the standard NIST frameworks, like your CSF, which is the cybersecurity framework, the special publication 800-82, which is the OT security special publication, and then 800-53, which is another security special publication. And then going a bit more into is the executive orders and federal directives. So there's been a lot of recommendations from the White House about cybersecurity in the energy sector. Towards the end of the Biden administration, the Office of the National Cyber Director released an energy modernization cybersecurity implementation plan, which is a 38-page plan on everything that the different energy providers. Pretty much everybody in the energy sector has to do, has like over 32 initiatives. And recently, President Trump came out with like an executive order to strengthen grid reliability and security. Didn't really go too deep into the actual cybersecurity part of it, just kind of like the Federal Power Act and emergencies allowing the Department of Energy to issue orders and have like a uniform methodology for assessing reserve margins and preventing the premature retirement of or fuel switching of certain generation assets. So going more into the EMCIP, as I mentioned earlier, this was like a roadmap for hardening the energy sector's cyber defenses. The main points of this EMCIP is that it's mandatory instead of voluntary. So a lot of times you'll have like these, they're just voluntary, where they doesn't really force them to actually like implement it. And this kind of pushed vendors and utilities to meet minimum baseline security guidelines versus, not having to prior, as well as requiring that security is implemented in the design phase of creating new energy devices. As well as they created this OT Defender Fellowship Program, which is in conjunction with the Idaho National Laboratory, which they grab a few capable individuals and bring them to the Idaho National Laboratory, and they get more skilled in OT defense, as well as having a lot more real-time monitoring across grid networks, not just the IT space. And
Yeah. Excuse me. So that's a lot of the security side of like all the compliance and standards that are inside of specifically like the North American electric grid. But now to actually get into how the electric grid kind of works as far as the transmission phase. First, we just have to cover some terms of like literally about electricity, because I was going over these things. If you don't know what voltage is, essentially you can think of it as just a force pushing electrons. The reason you need to know this is because you lose electricity over the transmission, but the higher you amp the voltage up, the less you lose. That's essentially all you need to know about voltage. Higher the voltage, less loss. But you can't use that really high voltage in normal appliance stuff. And then there's these 5 voltage classes. You just need to know what these. The top 2 are for our transmission phase, like long distance, a lot of power. And the bottom 3 are kind of for our distribution once it gets into the town or the city and stuff like that. Just wanted to briefly overview those. But now, the actual transmission phase. The electric grid we can kind of think of as having 3 categories. We're first going to cover the transmission, then we're going to cover the distribution today. And the third category is like the actual generation of the power. We're going to be splitting that up in the coming meetings because there's many different ways to generate power, whether it be solar, wind, through renewable resources, or through burning gas or some sort of coal or something like that, and then also, of course, nuclear. So to get into the transmission phase, the components that we have in here are we have these things called power transformers. We have 2 subcategories of this. We got the generator step-up and the step-down transformers, or just the step-up and step-down transformers. Now, a transformer changes the voltage either from low to high, high to low, step up, step down. Pretty simple. Then we also have these things called switch gears. Falls under this as circuit breakers. I'm assuming most of you kind of at least know what a circuit breaker is, because we have them in all the houses. You might flip the switch or whatever, and you have to go in there and flip it back. These are obviously in the industrial places outside of the homes, a bit more complicated and a bit larger, but they essentially do the exact same thing. When something gets drawn too much, it'll flip a switch and cut off the power. Then we have these things called isolators. These kind of work in conjunction with circuit breakers sometimes, not all the time. Their job isn't to disconnect the actual circuit, but their job is to make sure it stays disconnected. So say you have a tree fall down on a power line. Well, you don't want it to, because that'll first switch a circuit breaker, but sometimes those circuit breakers can automatically be coded to switch back online, and you don't want that if the power line is still down. So what you can have is these isolators, if detecting that breach in the line, can actually stop the circuit breaker from turning back all the way. Another thing, so inside of the transmission, we got these transmission substations. We have a step-up substation, step-down substation, and then a switching substation, or switching stations. So we have these transformers, right, that step up and step down, and these are the component level. But when working with the entire electric grid for modeling stuff, it's like not practical to be like, okay, over in Rochester, we're going to build like 800 of these step-up transformers and like some over here. So we kind of break it up to these substations, is what we call them. And essentially, what they do is through a whole bunch of different components and processes, either they step up, step down, or they're switching stations, which are in place to kind of break up the circuitry of the grid. Because, I mean, you've probably experienced this. If your power goes out, maybe somebody else's power didn't go out, like your friend that's in a different part of the town. And the reason for that is because we break up the grid into tiny little chunks so that if we lose power in one place, we don't just lose it everywhere. And at the transmission level, at the highest level, this is done with switching stations. But inside of like some of these transmission stations, first we have these instrument transformers. That's going to be this image up here in the top right. There's some instrument transformers. These transformers' jobs aren't actually to take the power itself and change the voltage from a low to high or high to low. It's to take the voltage or whatever reading it's getting from it and turn it into a sensor-readable amount of voltage, because they're really high voltage amounts at the transmission level. And so the instruments that we want to have to sense this, we just basically put these in to convert it to a really lot lower amount so we can have finer tuning onto that. Then we have protective relays. I mean, these are your IEDs, if you remember that from the first meeting, the intelligent electronic devices in your PLCs. These are your actual controllers. So we have an IED in the bottom right there. And so these are the things that are actually going to be making the decisions inside of these substations to do, switch on that breaker, switch off that breaker, increase the voltage, decrease the voltage, do all that type of stuff. Then you also have the circuit breakers that are a very key part of, they're like the actuator of the electric grid. So they're the thing that actually turns off these circuits, and that's one of the main things that the electric grid kind of does, is turn off and turn on circuits. So inside of the substation, we can kind of find these automation bay levels. If you can remember from the protocol networking meeting, was that 2 weeks ago? I think that was 2 weeks ago. Time flies. We can see kind of, I mentioned that there's this process level and then bay level. Nope, sorry, that's station, bay, and process level. That's to do with the IEC 61850 protocol. And essentially this is what's found in a lot of the substations for some of the components that are in there. So down at the process level, we have our switches and we have our actual components. I don't know why they called them C2s here. Yep, current transformer, potential transformer, circuit breaker, merging. So a whole bunch of these actual physical components that then go up to the switches, and then go up to the actual controllers, the IDs, the PLCs, then go up into more of our SCADA and all that stuff. But essentially, as you can see, taking a look at the grid, it's a very kind of like modular process. First, you have to look at the larger picture of, okay, how does we get power from here to here? And then we can kind of treat the substations as a black box for the most part. But it is important to know what's actually going on inside. Know what's going on inside of these stations, and so kind of this is a good diagram for understanding that if you want to take a look at that later. But as far as the transmission grid architecture is concerned, it's using a network system, which is like smart. There's lots of feeders. It's all interconnected. It makes the most sense because it's literally just how we think of the internet. So in this image we have our generator substation. This is a step-up substation that's connected to some sort of power generation. It's going to be sending its power over high voltage lines to a switching substation. Same here. So generation substations send their energy to switching substations, and they kind of form a mesh. And then they send them to step-down substations. And the black lines are representing the extremely high voltage class. And then the blue lines are that just normal high voltage. So step-down substations will also be connected to each other, but this is essentially what you can think about when you're thinking about the transmission phase of the electric grid, is you got your generation going to switching substations and then go to step-down substations. And now we get into the distribution phase, which kind of is the same thing. It's just all dealing with lower voltage, a lot less distances, so the types of equipment can be kind of less robust because you're not having so much voltage and current run through them. So some of the components we have here is we got distribution transformers. That's, if you're ever driving down, you see the little circular box on a power pole. That's a transformer. It's a distribution transformer, and its job is to deal with voltages that are a lot lower than what the other transformers have to deal with. And a lot of the time, they allow for remote connectivity to make sure that they're doing everything right. But like simultaneously, they're more advanced and simpler because they have a lot more remote config, but they have a lot less automation abilities that the other transformers do have. Then you got the voltage regulators, but that's not in this picture. But voltage regulators, essentially what their job to do is counteract voltage drop. I was talking earlier about how we have loss of electricity when we sense it over the wire at lower voltages. Well, now we're at these lower voltages because we're at the distribution phase. And so we actually need to add devices into the electric grid to actually counteract this voltage. We call those voltage regulators. Essentially what they do is they're a transformer that can step up and step down. And it has like a capacitor in it, so it has some extra features there. But that's all you need to know for voltage regulators. We also have fuses, which aren't too important for like actual security, but are really important for understanding how the grid works. Because fuses aren't, they're like a one-time use physical thing. You run too much electricity through them, it literally breaks the connection physically, and so somebody has to go in and replace them. This is a good attack surface for attackers though, because if they take out a lot of fuses, then it would require a whole lot of manual labor to go and replace them in all of the places across wherever they're going to burn out. You also have things called reclosers. These are essentially intelligent automatic circuit breakers. While they do differ from some of the more advanced circuit breakers that are doing things automatically, essentially they're just an intelligent, it does automatic circuit breaking. And their main purpose for the distribution phase is if a tree branch hits a limb, like doesn't like take down the entire power pole, but actually like touches the wire, that actually causes a short. And so these reclosers are really quick in detecting those and literally turn off the power for a brief second when the instant they detect a short, and when the tree branch comes off, it recontinues the pathway. So that's also why they have to cut off all the tree limbs when they get close, because they'll notice, oh, the reclosers are going crazy because the tree limb keeps hitting the branch. And then we have sectionalizers. These are essentially a small component that kind of does the same thing at the distribution phase that at the transmission phase an entire switching station does. They're just meant to make sure that if you have a fault somewhere, it can actually cut off that section, make it more granular for your control of what you turn off and turn on. This is the same for if it gets hit in like a storm, gets taken out, or if you're just doing basic maintenance. Now, the distribution grid architecture has kind of two types that they do. Radio system. This is the simplest and most common at the distribution level. It's also the least expensive. Literally what it is just like, they talk about it like it's a tree, but essentially it's you have your step-down substation that we saw from the transmission phase, goes to that step-down substation. Then the distribution phase begins. That sends power to the distribution substation. And then from the distribution substation, which is just even lower voltage, it's going to then send it in one wire to the house or the business or wherever you're sending the electricity to. It's also only one direction. A loop system is essentially just a radial architecture, just it gives you like one additional point of failure. So there's two paths. I mean, as you can see in that diagram, you have the step-down substation. You're going to have two distribution substations. They're going to be connected to each other, and they're both going to get sent to the house. So if one distribution substation gets taken out, you can still send power the other way. Yeah, it's also to isolate the fault segments better. So how do we do actually like management communication inside of the grid? Well, we got our good friend SCADA. This is going to be for your data collection, making sure you're actually doing your control and supervisory, and actually displaying your data, making sure you have a good way of actually displaying your data and visualizing it. And this is a very big part of the backbone of like large-scale operations, looking at the transmission phase of the grid, making sure all your stuff is actually working together. I'm not going too much into SCADA because we've covered it in a couple meetings. Then we have this thing called energy management systems, or EMS. This is advanced software applications. It also has automatic generation control, so generating the power, it'll automatically kind of generate how much. If you're running low on power because you're having an increased draw, it'll automatically tell the power plants, hey, give me more power. It also does a whole lot of network analysis, and by network analysis it means like a network analysis on the electricity running through the grid, not network analysis in the sense of like sniffing for packets or stuff like that. And it's also used a lot by the transmission system operators. So EMS is kind of your software that's used to control the transmission phase of the grid. And SCADA is kind of used everywhere and to combine them. Then we have our distribution management systems. I mean, pretty obvious where we use this one. It's in the distribution phase of the actual transportation of the electricity. So it's tailored for the distribution systems. It's also a counterpart to EMS. So you use EMS and DMS, one in the transmission, one in the distribution phases. Again, it has automation, has fault location, isolation, service restoration, so it can quickly locate where the fault is actually occurring and do all that stuff. It also has volt and VAR optimization, which without, electricity is a very complicated thing, but basically it optimizes how it's sending the electricity to have the least amount of loss. And then it also has the distributed energy resources, so it actually provides you with a nice catalog of all of your resources that are inside of your distribution network, which is really nice because a lot of the other tools in OT don't do that, so you have no idea what's actually going on, but this tool will actually automatically go and figure all that out for you, which is sweet. And it's also used a lot with solar power systems because with the, if you get a solar panel on your house, well, the grid kind of has to be like, okay, well, now we have a new source of power, but it's a variable source of power. What are we going to do with it? So DMS does a lot with trying to manage that and make sure the grid still operates at a optimum rate. Okay, questions about those two parts of the electric grid, the transmission, all that stuff. We got our power generation, goes on a step up or a generation substation, gets transmitted over the high voltage wires, those like massive, like power, they're not power pole structures. I'm forgetting the actual name of them right now, but the massive metal ones. And then they get put to step down and switching substations, and they get moved on to the distribution phase where it's going through the town, through the power poles, and then into your house. Okay. So that's all we wanted to cover for the transmission phase. But now we're going to talk about the OTSIG project. Yes.
A question about the substations. What was it, the loop diagram? What was it like?
It's a loop system.
You think that
This diagram's not a good diagram. I realize that now, because literally, if you lose a substation, then yeah, you can't. I don't know why I drew those arrows there. They should have been drawn crossing to the house.
Well, that's what I was thinking about. I was like, that's probably useless because you have to have like almost the squared amount of times of the size of the substation unit.
Yeah, no, looking at that now. But to be fair, that also can happen. So you will. There are actually some examples of this. I was looking at an actual network diagram of an electric grid in, I forget now. And so I was pulling that and putting it into the drawing software. But now looking at that, yeah, that is not actually loop architecture. That is a radial system architecture that they were like, you know what, let's connect the distribution subsystems, or substations.
I mean, it makes sense.
Any other questions?
Which part is like most attacked?
Which part is most attacked? Generally, it's going to be those step-down substations because, well, that's just what's been most attacked. Why? Probably because they're the most vulnerable, because they're generally remote, and so you have to have a lot of remote connectivity and being able to, as the company or the utility manufacturer, being able to actually go in and configure and make sure everything's going right and exfiltrate data. And so if you need that as a feature, well, then it's a good place for people to attack because, you can have access to it. Okay. So the OTSIG project that we're going to be doing, we kind of started it-ish last week. Created a organization on GitHub for the interest group. And the way we want to interact, if you want to join this interest group, there's the Discord server, which is in the resources announcement in the GridSec channel. For the project's Discord, and so then in there you can find more information about how to do it, and that's where you can send us your GitHub account and we can add you to this organization. We have this repository here, which is GridSecSim, which is simulation that we're going to be working on. We just have some very basic stuff in it right now. But the main thing is, if you want to actually interface and actually contribute to this project, you go to Projects and you go to here. Now, this is a Kanban board. If you don't know what that is, essentially, if you want to start a task, you look in the Ready category. I see Jared has already taken a task, but you click on one of the tasks you want to do, say researching simulating circuit breakers. There's a brief overview of what actually you have to do to make sure it's done, some overview of it, labels, time, all that stuff. And so you'd click here, you click assign to yourself, and then you just start working on that, and that lets other people know somebody's actually working on this task. And then you can just move it over to in progress. And then when you get done with that, put it in the comment and in review. There's this kind of GitHub project guide that explains a whole lot more. So essentially, we want you to assign yourself a task that you want to do. If you decide, actually, I did not want that task, you can unassign yourself from that task and move it back to being ready. The general workflow of kind of how the tasks are going to operate is we have the first task, which is like figuring out what do we actually need to simulate. So I already went ahead and did that. So it's in review. So I was like, okay, well, here's what we're going to need to simulate. Starting off, we're going to need to simulate the power transformers, the step up, step down, circuit breakers, IEDs, PLCs, the RTUs, voltage regulators, reclosers, and sectionizers. So then I went ahead and created all these tasks. Then kind of like step 2 is actually doing the researching how you're going to simulate this process. Essentially what that means is we're using Docker, and so you're going to have to find a way to simulate this component using Docker. Sometimes people have already simulated for it, and that's great. You can literally just take the Docker image if it's on Docker Hub, and it's like, well, you're kind of done. You're not entirely done. You're sort of done. But basically finding a couple of those, put any of your findings as just a comment to the task. That way anybody who wants to maybe help or just kind of checking in to see what's going on with the project can kind of read the comment and be like, okay, I know what that is now. Then after that, you actually have to start simulating that component. So you go on and you try and actually set up a Docker container, get the whatever you're trying to simulate functioning, and once it spins up and you kind of interact with it and you understand it, then you move on to the last part, which is actually making it work inside of the rest of the infrastructure. So sometimes you might come across like a piece of software that'd be like really great for simulating like only it, but it won't interface really well with other components other people have made. And so this last step, you know, you're gonna have to talk with other people who are simulating the components, but pretty much if you're running into an issue, just like message me or Lucas, because our kind of job here in this interest group is trying to keep everybody kind of on the same page, making sure everything's running smoothly. So if you're like, oh, I have this simulation here, but it doesn't work really well with this piece, this other person's component, we can kind of look at which one might be better, how to interface it, stuff like that, because we also have a lot of experience with trying to get them to mesh together, because components sometimes it takes a little bit of work. And so there's more details here if you want to read through that. This document can be found inside the project's Discord. There's a link to it in there. So yeah, is there anything? Oh, is there anything I missed? Oh, there's a whole bunch I missed. So GridSecSim, simulating the process of an electric grid. That's kind of the goal. We're going to be using Docker and GitHub. So I just showed you the GitHub part. There's the project board and that kind of like general workflow. Assign yourself, put it into that part, then put it into review once you're done with it, and then we'll just take a look at it. That way we can try and stay on top of everything that's going on and make sure we're still organizing it. That's the workflow. And then, okay, some important things to know when doing this simulation is we've already done, so we have this industrial network template, which we're not going to exactly use because the electric grid is kind of entirely different from what we simulated. But inside of here, actually we already moved it over here. We have some tools that make it easier to do a whole lot with like working with multiple Docker Compose files, because we want to split it up to have, right here, we already put the network folder in there. But that's going to control any of the networking that needs to be done, also deal with any of the Docker stuff that I need to deal with to make our simulations actually work with the Docker engine and the Docker networks. And then we have this git services.sh, which is just a simple script that'll get all the services and put it into a text file so that this cool script, tools.sh, can actually give you tab autocomplete on all of the services. There's documentation for how to use this inside of the docs folder. But if we just go into the network, currently all that's in there is this Docker Compose file. So if you've never looked at Docker before, please do. I'm not going to be explaining it. Like if you have questions, please ask. But Docker has some really good resources for learning. Again, there's more resources inside of the Discord on that. But this is sort of the two stuff that we've set up to make it run more smooth. So we have this God debug container, which we're going to be improving. But essentially, this is a container that you can exec into in order to have a bunch of nice just debug like commands and stuff pre-installed. Because sometimes when you exec into the container, if it's broken, it won't have like a text editor. And you'll be sitting there going like, oh, I want to read what this file is. And it's like, no, you're good. And you're like, no, but so this is really useful for actually being able to do a lot of debugging. We're going to put it in every network. And the reason for that is in order for a Docker network to exist, there needs to be a container that uses it. So that's its other purpose. Then we have this controller container. And so this container, what it does is on any container starting up while this container is running. So here's another thing. If you're running the GridSecSim project and you're running another Docker thing, the controller dude will he'll get messy and mess with your other project. Because what he does is on any container startup, he goes into that container, checks to see if it has the IP command installed. If it does not, figures out how to install it, installs that IP command, then changes the default route to one of our routers. Because we also have to make the routers in order to make the networking side of the house work. So if you're running into networking issues and you go into your container and it has the IP route of anything .250, we're setting all of the Docker routers to 250. Then your controller container is messed up. You can either manually change it or figure out what's going on with the controller container, make sure it's still running, stuff like that. But so that's that back end part. We have this controller container that's going to be updating all the default routes to point to our routers. We're going to define all of our networks inside of here, and we have God debug. Oh, this keyboard's so weird. So that's inside of the network. We're going to be having the routers in there, all the networks we're defining, stuff like that. And that's what we have in there for now. So that's the Docker backend with that controller, knowing how that works. Again, there's more docs to this that I'm just not going to go over, but this is a brief overview. And then also, of course, there's the Discord server for, not the RidSec Discord server, but for the project itself. That way we can just have a space where if you ever have any questions or want to contact somebody who's also working on the project easily, you can just do it in there. So yeah, we're simulating a grid. We're going to be using Docker. We're using GitHub, the organization. You got to ask to join, so just send your GitHub username or whatever to us in that Discord, and we'll just add you in. We're using the project board. There's that general workflow, and there's that Docker backend with the controller, container, and God debug, and the general structure there. Okay. Any questions about the project? Any things that I didn't explain very well?
How good would this project look on?
Yeah. So even if you don't, excuse me, even if you don't plan on doing a lot with this project, you still contribute something, because employers you tell them, oh yeah, I worked on helping simulate an industrial thing. They're like, tell me more, and you're like, oh yeah, so yeah, I'm doing this OT stuff, and they're like, what's OT? And then you tell them OT, and they're like, oh, that's cool. It truly, OT projects, aside from any other project I've done, caught all of the employers' interest way more than. So it's really good for your resume. Even if you just pop in, do one task, then you can say you did it. And you're also in the organization for any of the other random stuff we end up doing later on. Thank you, Jared, for reminding me to say that. Any other questions about where to start doing anything like that? Okay. Join the Discord, not only, the role join, but also the projects Discord if you plan on doing on that. Sign in if you haven't already. Next meeting, we're going to be looking at like actual power generation through a natural gas power plant, and we're also going to do some like checkups on the GridSecSim, make sure anything that's clear with that, stuff like that. So that's all we have for you today. It's a bit of a quick meeting, but yeah. If you have any questions about the project, you want to participate. Oh, question?
Question about the Cyberforce company.
Oh, I was going to say more about that. Yeah, ask your question.
So for the application, when should we have that submitted by?
So we need to submit by Friday. So preferably tonight. So the current, I forgot if we didn't mention this. So October 3rd, which is Friday. Yep, October 3rd, which is Friday, is when we need to submit the team to the competition.
Yeah.
It's 4 to 6 people, and so there's that. The actual competition dates are from the 14th to the 15th. We're going to be driving there because, like, we're asking for funding from the school and stuff, and they're like, maybe. And GridSec, they're like, we have a little bit. So we're like, okay, you guys can cover the hotel rooms. We're going to drive there instead of attempting to fly 6 people there, because that'd be expensive. And then also rent a car, which actually I don't think any of us could do unless we get somebody like over, 25? Who knows what the rental car situation is. But anyways, so we're driving there. We have a car that fits everybody.
So yeah, and we get access to the AWS environment a week before, like 10 to 12 days, just based off of like what I've seen from previous competitions. So the competition technically starts November 14th to 15th, but that full like 10 days prior is pretty much spent like preparing, like all of your services and like having everything secure before you actually get to the competition.
So just fill out that interest form. I think we're planning on leaving actually on the 13th. Then that way we can, because it starts the 14th in the morning.
Yeah.
So.
And it goes all day, 14th and 15th. So we'll probably leave on the 16th.
Yep. So leave on that Sunday. It's leaving on a Thursday. So competition starts on a Friday, Saturday, heading back on a Sunday. So that's the kind of schedule there. Yeah.
And if you want to volunteer, if you don't want to be on the team and have that huge time commitment, because it is a time commitment to be a part of the blue team, just because there's like a full library of things to look into and like learn about. So if you still want to be involved in the competition and don't want to have that same time commitment and you're not free during that time frame of November, then you can actually volunteer asynchronously for, I think, green team and red team or something like that. So
probably not red team, but I think you can do like green team, which is you can volunteer for
that's the users
if you want to be part of the competition by just helping out with the competition, doing stuff like that.
Yeah. So there's a bunch of ways you can get involved without having to actually go to the competition.
Yeah, having to actually physically travel to the competition.
And the biggest thing for the competition, I think, is just the time commitment to actually just put in to prep for it, really, more than anything. I think that's the biggest and most important thing, because it's a very kind of like niche kind of competition compared to other cybersecurity competitions, I would say.
Yeah, so preferably, if you're interested, fill out the interest form. By like tomorrow, we'll like message everybody who filled out the interest form, kind of try to give more details that we compile. If we get our responses back from the department or from the club about the funding, stuff like that, we'll try to get that to you, midday Wednesday, and then we can kind of go from there. Okay, that is everything I have. Unless somebody asks a question that somehow reminds me of something else. Okay, thank you all. Have a nice day.